You do it 100 times a day, right? You click a link. But have you ever stopped to think about the invisible, high-speed journey that happens in that tiny split second? I mean, how does a request from your laptop in London get all the way to a server in Los Angeles and back before you can even blink? Well, today, we're going to follow that data, step by step, on its absolutely incredible journey. So just picture it. You click a link, and poof, the page loads. It feels instant. But in that tiny fraction of a second, your request has just kicked off this wild adventure across a global network of undersea cables, switches, and routers. We're going to follow a single, tiny packet of data on that exact journey, from your device to a server, and see how in the world it finds its way. Okay, first things first. Our data can't just wander onto the internet by itself. No way. It has to get prepared for the trip. The best way to think about this is like sending a letter. You can't just write a message on some paper and hope it gets there. You've got to put it in an envelope, write an address, and add postage. In the world of networking, this whole preparation process happens in layers. This process has a technical name, encapsulation. But I just like to think of it as getting dressed for the journey. Your initial request, that's the core message. First, the transport layer wraps it in something called a TCP segment, adding a port number. Think of that port number as the specific apartment number for the app on the server. Then the network layer wraps that in an IP packet, adding the global IP address, which is like the building's main street address. And finally, the data link layer adds the last wrapper, an Ethernet frame, with the local address for the very next device it needs to talk to. See, each layer adds another crucial piece of the address. All right, so with our data packet all dressed up and ready to go, it starts the very first leg of its journey, the local network adventure. Before it can even think about hitting the superhighways of the internet, it has to navigate your home or office network to find the front door, which is your router. So, to get around on this local network, devices use something called a MAC address. Now, unlike an IP address, which is kind of like your home's mailing address and can change, a MAC address is permanently burned into the network hardware itself. It is a globally unique ID. So, if the IP address gets the data to the right house, the MAC address is what finds the specific person inside that house. It's how devices talk to each other directly on a local level. And that leads to a really good question. Your computer knows the IP address of the router. That's its gateway to the internet. But it doesn't know its MAC address, its specific hardware name. So how does it find out who to talk to directly? It can't just send the packet out into the void and hope for the best. The solution is actually surprisingly simple. It uses the Address Resolution Protocol, or ARP. Your computer basically shouts out to every single device on the local network, "Hey, who has the router's IP address?" Every device hears it, but only the router replies, saying, "That's me, and here's my MAC address." Your computer then saves that info in a little cheat sheet called an ARP table, so it doesn't have to ask again for a while. Pretty cool, right? It's just a quick local chat to find the right recipient. And this slide really shows you how much local networking has evolved. You know, back in the day, devices were connected with these things called hubs. A hub was simple. Maybe a little too simple. Any data it got, it just shouted out to every single device connected to it, which created a ton of unnecessary noise. A modern switch, though, is much smarter. It listens in on that first ARP conversation and actually learns which MAC address lives on which physical port. So from then on, it sends data only to the device that's supposed to get it. It turns a loud, crowded room into a series of private, super efficient conversations. So our packet has successfully found the router. It's now sitting at the edge of the local network, ready for the main event, crossing the vast, interconnected global network we call the internet. This is where the real fun begins. This is where that IP address we added earlier becomes the absolute star of the show. While the MAC address was all about local delivery, the IP address is for global routing. It's the full-blown mailing address that tells routers all over the world where this packet is ultimately trying to end up. And it's cleverly divided into two parts, a network ID, which is like the city and the street, and a host ID, which is like the specific house number on that street. Now, to manage the millions and millions of devices online, not all networks are the same size. IP addresses are organized into these classes. You've got Class A for giant organizations. We're talking huge. Class B is for medium-sized networks. And Class C, which you can see here, is the most common for small networks, like the one in your home. This whole structure just helps keep the internet's massive global address book nice and organized. So, how does our packet actually navigate this global system? Well, it's all thanks to routers. Routers are basically the postal workers of the internet. They don't need to know the entire path from start to finish. Nope. They just need to know the next best step, or hop, to send the packet to get it a little bit closer to its final destination.
And they make this decision by looking at a map called a routing table. Let's break down what a router is thinking. When a packet heading for a website shows up at your home router, the router looks at the destination IP. It checks its internal map and asks, do I have a specific route for this? For a public site like Google, the answer is almost always no. So it just sends the packet to its default gateway. It's one connection to the wider world, which is a much bigger router at your internet service provider. That ISP router does the exact same thing, forwarding it to another and then another, hopping all across the internet until, finally, it arrives at the right network.
And just like that, after a whole series of high-speed hops across the globe, our packet has arrived at the destination server's local network. The hard part of the journey is over, but now the message needs to actually be delivered and understood. It is time for the unpacking. This process, called decapsulation, is the exact reverse of getting dressed. The destination server gets the Ethernet frame and just strips it away. Then, the operating system looks at the IP packet, confirms the address is correct, and strips that away. Finally, it looks at the TCP segment, reads the port number, in this case the port for a web server, and delivers the original, unwrapped request to the correct application. The message has arrived, safe and sound. Now, all this time, we've been talking about TCP. Think of it as the super reliable, careful delivery service. It guarantees every single packet arrives, and in the right order, which is absolutely essential for things like web pages and emails. But there's another option, UDP. And UDP is all about raw speed. It doesn't make any guarantees. It just blasts the data out as fast as it possibly can. This is perfect for video streaming or online gaming, where a single lost pixel is way less important than keeping the action smooth. It's that classic trade-off. Do you want reliability or do you want speed? So, we've followed a single request from click to delivery. We've seen all these layers of addresses, local shouts, and global hops. It's a lot of technical detail, I know. So let's zoom out and look at the big picture to see why this elegant, layered system is just so important. So here's the real takeaway. This layered design is the absolute genius of the internet. Each layer has one very specific job, and it doesn't have to worry about what the others are doing. MAC addresses handle the local neighborhood, IP addresses handle the global postal service, and TCP handles that final delivery to the right desk inside the building. But the most incredible part? This entire complex dance happens millions of times a second for billions of people all over the world completely invisibly. It's just amazing. All of this, the wrapping, the shouting, the global hops, the unwrapping, it all happens in less time than it takes you to blink. It is an invisible symphony of protocols and hardware working in perfect concert. Which kind of makes you wonder, as technology keeps pushing for even greater speeds, which part of this incredible, invisible journey will be the next one to get a supercharge?